this video, we're going to look at regression. So there's a difference between correlation and regression. Correlation, which we talked about in the last video, looked at the relationship between two variables, and regression does as well. So there has to be correlation in order to do a regression. So regression is where we are going to attempt to predict values of one variable using the other. And I'm just trying to figure out where I went here. Okay, just making sure I'm on the right track. All right, so the difference between correlation and regression is that we are identifying in regression one variable we're going to use to predict the other. In correlation, we simply said there was a relationship between the two of them. In regression, we pick one variable we're going to call the independent variable, and then we are going to try to predict values of the other variable we're going to call the dependent variable. When we get to machine learning and some of the data analytics methods, they often use the term predictor variable for the independent variable because it is the one that is a predictor of the other one. And then we have the variable that's being predicted, the response variable. We look at regression, particularly in experimental design. We have a random assignment into two groups. We have the test and we have the control. And the idea here is that we want to be able to predict the outcome of the test group versus the control group. We're saying there should be a difference because of what is happening with the independent variable. In correlation, there is no independent variable. We don't distinguish between the two different variables. We're simply looking at the relationship between the two of them. One isn't assumed to kind of have an impact on the other. So correlation, no causation assumptions. Regression, we're starting to get a little bit more towards that idea of causation. If we add in that experimental design components, we're getting even closer to trying to look at what if we manipulate one variable, does that cause change in another? So combine that experimental design with the regression, and then you start to get closer to causation. Okay. The classic correlation situation involves no obvious independent variable, just two dependent variables depend on each other. The researcher is primarily interested in assessing the strength of the relationship. Both variables are free to vary because their values are not selected in advance, as opposed to the more classical regression model, which is one dependent variable and one or more independent variables. So right now we're going to look at one predictor variable and its impact on that response variable. So one independent and one dependent. Later, as we get to our predictive prescriptive analytics, we'll get into multiple variable regression, and that's when we have multiple independent variables. So we'll come back to that topic later as we get to more complicated models in other videos. All right, so the value of the dependent variable for a given level of independent variable. So we're going to change the independent variable, see what happens to the dependent variable. And we're interested in changing the one variable to see the impact of the other. As I said, we're trying to get to that idea of causation, not just correlation. So we're going to try to predict what we call Y. So one variable is going to be the dependent variable. We'll call it Y, and then X is the independent variable. So X is the one we manipulate. Y is the one that it's free to vary, and we see what happens. We're trying to come up with here a linear regression model. Our linear regression model says we have an estimate for Y, and it is going to be a function of, we'll call it B naught. And that will be the intercept. So there's an underlying value of that dependent value Y separate from the independent variable X. And then a portion of the value of Y is dependent on what is happening with X. And this is the same, if you remember your initial graphing, say in high school, you did mx plus b to graph a line, and this was the slope, and this was the intercept. This is the same thing we're doing here. This is the slope. And this is the intercept. Okay, so it's the same thing for finding a line like you did when you did some early graphing, say in high school. So when it comes to our regression, we're looking for the line of best fit. So we're going to take our data and we're going to try to come up with a line that represents both the correlation. Remember, correlation shows strength and direction. Okay, and at the same time, what we're going to be doing is looking for the line that minimizes this difference between the points and the line itself. So the difference between the points and the line is what is called a residual. So the residual is the difference between the actual value of y and our line of best fit, our predicted value. So we're taking our actual minus our predicted. And we'll come back to this when we do forecasting. Another term for residual is measurement error when we're doing forecasting. We'll use residual as the term used in regression. But again, we're just taking the actual minus the predicted to see how far off our model is from those actual ones. So we want to choose a line of best fit that minimizes that difference between the actual and the predicted. It's going to take into consideration that variability in the x-axis values and the y-axis values, and that line of best fit is going to be our predicted y's, our y-hats. Okay. The underlying here where we're trying to find this line of best fit is based on the principles of least squares. So if we take our residuals squared and we add them all up, we're trying to figure out how to minimize that total amount of those residuals squared. One of the reasons we look at residuals squared is because sometimes our actual is going to be more than our predicted, so it's positive, and sometimes our actual is going to be less than our predicted, so it's negative. And we are looking for not just those to cancel out, but we also want it to be that we want to be in between them, but we also don't want any particular number to be like way far off, right? That squaring is going to then allow it to be impacted more so by observations that are really far away, okay? Instead of if we just average, then it's not as impacted by it. Okay, so this principle of least squares is going to help us to find what is the slope and the intercept. So our slope here is going to be our our intercept is going to be b naught, and our slope is going to be b1. Slope being the change in x, right? So if you found slope, it was rise over run. So here, change in y over our change in x. So this is x, this is y, this is our y hat estimate. We're going to say even if x is nothing, there's still some underlying value of y. As x increases, y increases if we have a positive slope. And that slope is going to be b1, which we're going to get from that change, rise over run, to give us what that b1 is. So it's the change here in y, divided by the change in x. Okay? So we're going to use that to find our slope and our intercept. All right, this goes through a bunch of math that we're not going to do. I'm just going to show you how to do it in Excel and in Python, because this is not a math class. Yeah, so you don't want to do any of that stuff. All right, so let's go in Excel. Okay, let's look at repairs. All right, so we have the age of, I believe, their vehicles. Let me just scroll down to wherever I put this problem set here. somewhere, maybe. Who knows? That is it. Here we go. Okay, let's first find the correlation between repair costs for Sparta and the age of the Sparta. So here we have these different vehicles. We want to find the correlation, and then we want to see if we can use the age to predict the repair costs. So let's do a couple things here in Excel. All right, so first, let us plot. All right, so if I want to plot this information, insert scatter plot. Now, notice here that the age is on the vertical and the repair cost is on the horizontal. I want to predict the repair cost using age. I believe that's what I want to do, right? Yeah, okay. I want to predict the repair cost using age. So the idea is the older it is, the more it's going to cost to repair. Okay, so I want to use age to predict repair costs, which means this scatter plot is incorrect. If I was just looking at correlation, it wouldn't matter, but I want to use age to predict repair costs, which means age needs to be on the horizontal. So if I am in the full version of Excel, not the one in the web browser, then I can right-click here and go select data, and I can remove these and decide what I want to be the X and the Y axes. So the X axis I want to be age, and the Y axis I want to be repair cost. I want to predict repair cost based on age. And then I hit OK and it will flip it for me. If I am in Excel, that is in the web browser, the dumbed down version of Microsoft 365, in order to get this graph, what I need to do is right click, insert a column to the left, move age over, and then highlight them and insert the scatter plot, because it doesn't allow that extra feature of specifying what's on the X and Y axes in the dumbed down version of Excel, in which case age has to be the first one and then repair cost has to be the second one. You can also, if that makes you more comfortable, you could just flip them and do it that way too, instead of doing right click, select data. Up to you. All right, so we have this relationship here. We want to build a line of best fit that is going to add a best line, and then it is going to give us that forecasted value. We can find the correlation. Remember, that's Pearson, open parentheses. It doesn't like that I bumped it, so go there. If you're just doing correlation, it doesn't matter which one you're doing first, so you could just highlight one, then the other. And here we get a correlation of 96%, or sorry, get a correlation of 0.96. That's R, not R squared. All right, so we want to do some regression. When it comes to regression, there's a couple different things you can do in Excel. So we could go to data and the data analysis tool pack. Remember that if you want the data analysis tool pack, if you're on a Mac, go up to the top menu where it says tools, Excel add-ins, and you can then select the tool pack. If you have a little icon right here under the data ribbon, this also allows you to initiate this tool pack. But if you've never installed it before, it may not be there. If you are on a Windows machine, then you should have a tab to the left, a ribbon to the left here, where it's the Excel. You go in, hit Other, and then you can do the add-ons. I'm just currently running this demo on a Mac. Some of my other videos, if you want to check out my other videos, some of them are doing the same regression models. We do predictions, forecasting, some of those models. In Excel, I have those and they're on Windows machines, so you can see the similar process. All right, so we want data analysis tool pack. There is a regression in the data analysis tool pack, so we can hit OK. Inside of that data analysis tool pack, we have to specify what is Y, so this is Y, and we have to specify what is X. Okay. We will want to look at residuals, so we can totally give us that. Our linear regression is going to assume normality, so give us a normality plot as well. Let's do that. and we want an intercept. This constant is 0. That's where you're forcing the intercept to be 0. We want an actual intercept, so we don't want to do that. Okay, so it's going to output a bunch of stuff. We're going to talk about how to use it in a moment. But let's start with some basics. So what this is giving us is it's giving us an R squared of 0.92. So in our previous video, we talked about how R, the correlation, can't be explained as a percentage variability in one variable that explains another. R squared does. So an R squared of 0.92 says 92%, let's go back to repair, 92% of the variability in age explains the variability in repair costs. Okay, so R squared does tell us about that percentage that is explained. And this is what is called the coefficient of determination, R squared. It is found by squaring the correlation coefficient. So it tells us the percentage that is explained by the model. Percentage of variation of y that is explained by the variation in x. Okay. So in fact, if we went back, equals, take this and square it, we get 0.92. And that's where, if I go back to this other page, that's where that 0.92 came from. It is the R you found before squared. All right. The other piece that we want to look at is we want to look at our variable x, and we want to check and see if the variable x can be used to help explain some of the variability in y. So the first check is R squared, and it says that x actually explains 92% of the variability in y. So when you look at R squared, you're looking for one that's about 80%. Higher is even better, but you didn't necessarily want to add more complications and make the model even more complicated by adding more variables, or we're looking at predicting over time or complications to the model just to get R squared higher. An R squared of 0.8 is good enough. Okay, we have an R squared of 0.92, so X, our age, really does a good job of explaining the variability in the cost of repairs. So model is nice there. We can also check here. Here we have confidence intervals. And our confidence intervals are showing us the upper and lower bounds for that X. If X really had no ability to, or told us nothing about Y, if the age really told us nothing about the cost of repairs, then what we would have is that we would have this here span 0. And you can see it doesn't span 0. You can see these are all positive. So the upper and lower bound of our confidence interval says the impact of X here is having a positive impact. Okay. It is statistically significant in the model. Notice that p-value there has that E with the negative 0.05. We talked about that before. That means there's technically, we moved the decimal place 5 places to the left. So this is 0.00001 is what that actual p-value is. So it's super small. And because it's super small, it's less than alpha. That means that our X is statistically significant in the model for predicting what we have here as the value of, or the repair costs. Okay, so right off the bat, we have that. The other thing we want to do is actually define the model. So what is the model? The model is going to be y equals, and this is actually y hat, and it is 77.5. That's the coefficient you get right here, plus 57.4 times whatever x is. So we can then actually predict the cost for a certain age car. So we could, for example, say, well, what if the car is 4 years old? Then 77.5 plus 57.4 times a 4-year-old car, the cost of repairs in this particular case would be $307. Okay, so we plug into X a different year and we get a different predicted cost. The residuals here are the differences between the predicted value of the cost and the actual value of the cost. So how far off is the model for all these different observations? And that is what is plotted here in this residual plot. The difference between the actuals and the forecasted model. Okay. I'm just going to take a step back here. Now, we can go into more detail in terms of interpretation and analysis of the regression model, which we will do in just a moment. But first, what I'm going to do is show you how to do the same thing in Python. Okay? All right. So let's go in. Just quick reminder, drstephpowers.github.io/BIA. And from there, we are working here in the regression workbook. It is actually the same workbook we've been doing confidence intervals in, so it should look kind of the same. Opening Google Colab. Don't forget, you will also need the Stats 3. And make sure you download it, dump it into your Google Drive, because you'll need that. And then once you are in Google Colab in your file, again, make sure you're logged in, make sure you've saved a copy into your drive, and then import pandas as PD, link your workbook to your Google Drive so that you can then import those Excel files that you just tossed somewhere into your Google Drive. Which means, if we go down, sorry, got to figure out where we're at. Repair costs. All right. So wherever you located that repair in your Google Drive, you will then need to tell it where to go. So my statistics 3 file, I want the repair file or tab within that. Mine is located inside of a folder called BIBA Handbook and inside a folder in that called Appendix. So this line of code here says use pandas to read the Excel file, and here's where that Excel file is located in my drive. So this part here is the part you will change to match where it's located in your drive. What's the name of the folder it's in, and if it's in a folder inside of a folder, specify. We want the sheet name repair because we're pulling the data set from that. And I think I named something else X4, but you can call this whatever you want. So if I just run this as X4, oh, must have timed out. No pandas. Okay, import pandas as PD. Link. Okay, let me go into my data here. And somehow I got rid of the D, so let's get rid of that. Oh, that's why. I don't know. That's missing in yours. Make sure you fix it. Read_Excel. All right, load her in. Show me the first 5 rows so it looks like what I expect to see. First steps, create a scatter plot. Let's be able to see it. Import matplotlib.pyplot as PLT. If you've already imported it before and are running this, you don't have to do it again. I just keep putting it down so that we don't forget, and you get an error and you can't figure out why it won't run. Well, it won't run if you don't have the package installed. And then what we're going to do is then plot it. So I'm just going to grab this same code from above. And here I am pulling from X4 something called repair costs. All right, it's unhappy because I put that in the wrong place. And then X4 age. Now I actually have it backwards, right? Because what I want is I want to use age to predict repair costs. So I want to put age on the horizontal and repair costs on the vertical. And then my x-axis is age. X is the horizontal. Y is the vertical. Y is what you want to predict. So here we have our graph, our scatter plot. And then we want our Pearson R. Look, it's already telling me what to do. X4 age, X4 cost. Yeah, that's really what I want. So just give that to me. AI is trying to interpret what analysis I'm trying to do. Getting better every day. And we can see that the p-value is less than alpha. And our alpha, if we believe that as age increases, repair costs increase, then our alpha is a 0.05. Our alternative hypothesis is that rho is greater than 0, that there is a positive relationship here, and we can see this p-value is super tiny, less than alpha. We know that because the part my head is covering up is the E negative 0.05, and so we can reject the null hypothesis and state that the correlation is positive. Okay. Now we want to use that to come up with our regression. Now there's a bunch of code here, and I'm going to do a little bit out of order just because there are additional pieces that I can show you where things come from. And so if you want to ignore all that stuff, the basic regression is going to be this code right here. It is going to fit an ordinary least squares regression, and it is going to try to predict y using x. And then you specify your data set, and we're going to fit that model. So this is the line to get your regression, and then the summary gets the basic output. So I'm going to come back to these other sections. In order to do that regression, I need to import statsmodels.formula.api as SMF. Okay, this particular one will then give me a coefficient. It'll give me a intercept and the slope, and then tell me my R squared. So that's what that is for. We will use these other packages that you see here. Import statsmodels.stats, and we'll call it stats for short, is going to give me this descriptive statistics I'm going to refer to in a moment after we do our regression. And then import statsmodels.api as SM. We'll also use that when we're looking at our assumptions, right? We're looking at things like QQ plots and stuff. So really right now we're just using this top one, but I might as well import all of them. Okay. And I am going to rename, just for simplicity's, I'm going to rename from my data table X4, I'm going to rename the columns. Repair cost is going to be Y, and age is going to be X. That way I remember what it is I'm predicting and not predicting. And so I'm just giving these new names. So when you do something like this, then what I've created here, reg.head, is a table that instead of saying repair cost and age, says X and Y. Okay, that's all I've done. All right, skip that, come back. Okay, so our ordinary least squares regression, I've given it a name. I'm going to use the package SMF. It's going to do an ordinary least squares regression. It is going to predict Y using X, and my data table I called reg for regression. So if you do this process and rename your variables so that you now have a table that looks like this with your data, then you don't have to change anything about this line of code for your data set. You have Y, and that Y is going to be predicted using X, and the data table is called reg for regression, and we're going to fit the model. Run this, do the summary. So give me the summary of what I called OLS_reg. Here's that R squared. So X, our age of our vehicle, explains 92% of the variation of the repair costs. Okay, that's this R squared here. Here is my coefficient of the intercept and then my X. So remember, if we go back in Excel, the formula was 77.5 plus 57.4 times X. you get the exact same formula from Python here, 77.5 plus 57.4 times x. So that is your regression equation. We can look here, as I talked about before, you can look at the confidence interval that goes with age, x. Notice that these are all positive, that they don't span 0. That tells us that age is a statistically significant variable for predicting our repair costs. Okay, we can also see that the intercept here, that's the value when x equals 0, is also statistically significant. Doesn't span 0, it has a positive relationship. So even if there was no age, if it was brand new, there would still be some underlying repair cost. And then as age increases, the repair costs go up. That's what you're getting from here. Okay. All right. So, too many things open. So what we've talked about is the basics of creating that regression and being able to then come up with a formula. This formula here, to be able to then say, if I put in a number for x, I can then predict the value for y. In our next video, what we're going to do is look at all of that other reported data, whether you're in Python or Excel, to make other statements. And then we'll have another video to look at the assumptions, QQ plots to assess normality, looking at residuals to make sure we have the right model. So we're going to break this into pieces because these videos are getting too long. So next video, we'll dive deeper into the output from Excel and Python.